NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial. Today we're going to simplify a complex algebraic expression step by step. Let's look at our example. We need to simplify the expression. Open parenthesis 2x squared plus 4 close parenthesis squared times open parenthesis x squared minus 3 close parenthesis squared. Let's simplify this step by step. First, we'll factor the first expression. We can rewrite 2x squared plus 4 as 2 times open parenthesis x squared plus 2 close parenthesis. Next, we expand the power. When we have open parenthesis 2 times something close parenthesis squared, we can rewrite it as 4 times open parenthesis that's something close parenthesis squared. So we get 4 times open parenthesis x squared plus 2 close parenthesis squared times our second expression. Now, we can factor the entire expression. We notice that we have open parenthesis x squared plus 2 close parenthesis squared times open parenthesis x squared minus 3 close parenthesis squared. This allows us to create a common term open parenthesis x squared plus 2 close parenthesis times open parenthesis x squared minus 3 close parenthesis, and then square the entire expression. Now, we'll use the common term identity. We have the product of x squared plus 2 and x squared minus 3. Let's recall the common term identity. Open parenthesis, a plus b close parenthesis times open parenthesis, a plus c close parenthesis equals a squared plus a times open parenthesis, b plus c close parenthesis plus b times c. In our case, a is x squared, b is 2, and c is negative 3. Next, we need to square the expression inside the parentheses. Let's use the square of a sum formula, which states that open parenthesis a close parenthesis squared plus open parenthesis, b close parenthesis squared plus open parenthesis, c close parenthesis squared plus 2 times a times b plus 2 times a times c plus 2 times b times c, where a is x to the fourth, b is negative x squared, and c is negative 6. Now, we simplify the expanded expression. X to the fourth squared is x to the 8th power. Negative x squared squared is positive x to the 4th power. Negative 6 squared is positive 36. 2 times x to the 4th times negative x squared is negative 2x to the 6th power. 2 times x to the 4th times negative 6 is negative 12x to the 4th. 2 times negative x squared times negative 6 is positive 12x squared. Let's group like terms to simplify further. We have x to the 8th, negative 2x to the 6th power, x to the 4th minus 12x to the 4th, which gives us negative 11x to the 4th, 12x squared, and 36. Finally, we distribute the factor of 4 to each term inside the parentheses. 4 times x to the 8th is 4x to the 8th. 4 times negative 2x to the 6th is negative 8x to the 6th. 4 times negative 11x to the 4th is negative 44x to the 4th. 4 times 12x squared is 48x squared. And 4 times 36 is 144. To present our answer in a standard form with descending powers, we write it as 4x to the 8th minus 8x to the 6th minus 44x to the 4th plus 48x squared plus 144. Let's summarize what we've learned in this example. We simplified a complex algebraic expression by first factoring out common terms, then using algebraic identities like the common term identity, then expanding using the square of a sum formula, and finally combining like terms and distributing factors. These techniques are fundamental in algebra and can be applied to many different problems. Remember to work step by step and keep track of all terms carefully. We have a squared plus 1 multiplied by a squared minus 5 multiplied by a to the 4th plus 4, a squared plus 5. Our goal is to expand this expression using algebraic techniques. To solve this problem, we'll use the common term identity. This identity states that for any expressions a, b, and c, the product of a plus b, and a plus c equals a squared plus a times the quantity b plus b times c. Following the steps shown in our algorithm, we'll start by grouping the first two factors. We can rewrite this as the quantity a squared plus 1 times a squared minus 5, and then multiply by the third factor a to the 4th plus 4 a squared plus 5. Now, we'll apply the common term identity to the first grouping. If we let a equal a squared, b equal 1, and c equal negative 5, we can apply our common term identity. Applying the identity to our expression, we get a to the 4th minus 4 a squared minus 5, multiplied by our third factor, a to the fourth plus 4 a squared plus 5. Looking at our expression, we can recognize that we have a difference of squares pattern forming. Let's rearrange to emphasize this structure. We have a to the fourth minus the quantity 4 a squared plus 5, multiplied by a to the fourth plus the quantity 4 a squared plus 5. Now we can clearly see we have a difference of squares, which has the form a squared minus b squared, where a is a to the fourth and b is the quantity 4 a squared plus 5. Using the difference of squares formula, a squared minus b squared equals a plus b times a minus b. Let's simplify. A to the fourth squared is a to the eighth, and we need to expand the quantity 4 a squared plus 5 squared. To expand the quantity 4 a squared plus 5 squared, we use the formula a plus b squared equals a squared plus 2a b plus b squared. This gives us 16a to the fourth plus 40 a squared plus 25. Now we substitute this back into our expression. We get a to the eighth minus the quantity 16a to the fourth plus 40 a squared plus 25. Therefore, our final answer is a to the eighth minus 16a to the fourth minus 40 a squared minus 25. To summarize, we expanded the expression by first using the common term identity to simplify the first two factors. Then we recognized a difference of squares pattern and used that formula to further simplify. Finally, we expanded the squared binomial term and combined everything to get our final answer. This method shows how identifying patterns like the common term identity and difference of squares can help us tackle complex algebraic expressions efficiently. Welcome to our video where we'll verify that the quadratic formula actually works. We'll verify that when we plug in the solutions from the quadratic formula back into the standard form of a quadratic equation, we get an identity. Let's see how we can solve this step by step based on the given algorithm. We'll start with the standard form of a quadratic equation and show that the solutions from the quadratic formula satisfy this equation. Let's start by recalling the quadratic formula. The solutions to the equation ax squared plus bx plus c equals 0 are x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now, let's verify that these solutions actually work by substituting them back into the original equation. We'll substitute these values for x into ax squared plus bx plus c and verify that we get 0. First, we'll substitute the two solutions into the left-hand side of the original equation. We have a times x plus b plus square root of b squared minus 4 ac over 2 a times x plus b minus square root of b squared minus 4 ac over 2a. Now, we'll use the common term identity to expand this expression. The identity states that the product of a plus b and a plus c equals a squared plus a times the quantity b plus c times c. Let's apply this identity to our expression. We'll have a times x squared plus x times the quantity b plus square root of b squared minus 4 ac over 2 a plus b minus square root of b squared minus 4 ac over 2 a plus the product of the two terms b plus square root of b squared minus 4 ac over 2 a times b minus square root of b squared minus 4 ac over 2a. Now let's simplify. First, we can simplify the coefficient of x. Adding the fractions inside the parentheses, we get b plus square root of b squared minus 4 ac plus b minus square root of b squared minus 4ac, all over 2a. This simplifies to 2b over 2a, or just b over a. For the constant term, let's multiply the two fractions. We get b plus square root of b squared minus 4 ac times b minus square root of b squared minus 4 ac over 4 squared. Let's continue simplifying. When we multiply the numerators in the last term, we get b squared minus b times square root of b squared minus 4 ac plus b times square root of b squared minus 4 ac minus the square root of b squared minus 4 ac squared, all over 4 squared. Notice that the middle terms cancel out, and the square root of b squared minus 4 ac squared is just b squared minus 4 ac. So we have b squared minus 4 ac over 4 squared, which simplifies to 4ac over 4 squared, or c over a. Now let's simplify further. We have a times x squared plus b over a times x plus c over a. Distributing the a, we get a x squared plus bx plus c. Let's look at our example. We need to find the product of x squared minus 3x plus 1 times x squared plus 5x plus 1. We'll solve this step by step based on the algorithm shown. Our first step is to rewrite the expression. We'll keep the first binomial as x squared minus 3x plus 1, but we'll rewrite the second binomial as x squared plus the quantity 5x plus 1 in parentheses. For step 2, we'll apply the common term identity. This identity states that when we have the product of a plus b times a plus c, it equals a squared plus a times the quantity b plus b times c. In our case, a represents x squared, b represents negative 3x plus 1, and c represents 5x plus 1. Now, let's simplify the expression. First, x squared becomes x to the fourth power. Next, we combine like terms inside the brackets. Negative 3x plus 5x equals 2x, and 1 plus 1 equals 2. So the middle term becomes 2x plus 2 times x squared. And we leave the last term as negative 3x plus 1 times 5x plus 1 for now. In step 4, we multiply the terms. The first term remains x to the fourth. For the second term, we multiply 2x plus 2 by x squared, getting 2x cubed plus 2x squared. For the third term, we multiply negative 3x plus 1 by 5x plus 1, which gives us negative 15x squared minus 3x plus 5x plus 1, or simplified as negative 15x squared plus 2x plus 1. In our final step, we combine like terms to get our answer. We keep x to the fourth and 2x cubed as they are. Then we combine the x squared terms. 2x squared plus negative 15x squared equals negative 13x squared. Next, we combine the x terms. Negative 3x plus 5x equals 2x. And finally, we keep the constant term, which is 1. So our final answer is x to the fourth plus 2x cubed minus 13x squared plus 2x plus 1. This is the complete expansion of our original product. Let's recap what we've learned. We started with two binomials and used the common term identity to organize our multiplication. We carefully expanded each term, applied the distributive property, and combined like terms to reach our final answer. This technique can be applied to multiply any two polynomials. We have a complex expression that we need to simplify. A minus 2 squared times a squared plus 4 squared times a to the fourth plus 16 squared times a squared plus 4a plus 4. Our goal is to simplify this expression by applying various algebraic techniques. Let's begin our simplification journey. First, we notice that a squared plus 4, a plus 4 can be rewritten as a plus 2 squared. Also, we can use the fact that a minus 2 squared is equal to a squared minus 4a plus 4. So, our expression can be rewritten as a squared minus 4a plus 4 times a squared plus 4a plus 4 times a squared plus 4 squared times a to the fourth plus 16 squared. Now, we can factor the first two terms differently. We can rewrite the expression as a squared minus for a minus 4 times a squared plus for a plus 4 times a squared plus 4 squared times a to the fourth plus 16 squared. This can be further simplified as a squared minus for a minus 4 times a squared plus for a plus 4 times a squared plus 4 squared times a to the fourth plus 16 squared. Now, we'll use a common term identity to simplify further. The identity states that a plus b times a plus c equals a squared plus a times b plus c times c. This will help us expand the product of the first two factors. Let's apply this identity to our expression. In our case, we can identify a as a squared, b as 4 minus 4, and c as 4a plus 4. After applying the identity, we get a to the fourth plus for minus 4a plus 4, a plus 4, times a squared plus for minus 4 times 4a plus 4, times a squared plus 4, squared times a to the fourth plus 16 squared. Now, let's simplify inside the first bracket. We have 4 minus 4, a plus 4, a plus 4, which simplifies to 8. Also, 4 minus 4, a times 4 plus 4, a can be expanded as 16 minus 16a squared. After these simplifications, our expression becomes a to the fourth plus 8a squared plus 16 minus 16a squared times a squared plus 4 squared times a to the fourth plus 16 squared. Let's continue simplifying. Inside the first bracket, we have a to the fourth plus 8a squared minus 16a squared plus 16, which simplifies to a to the fourth minus 8a squared plus 16. So, our expression becomes a to the fourth minus 8a squared plus 16 times a squared plus 4 squared times a to the fourth plus 16 squared. Let's factor the first bracket. we can rewrite a to the fourth minus 8a squared plus 16 as a squared minus 4 squared. This gives us a squared minus 4 squared times a squared plus 4 squared times a to the fourth plus 16 squared. Let's look at our expression more carefully. We have a squared minus 4 squared times a squared plus 4 squared. We can recognize that a squared minus 4 times a squared plus 4 equals a to the fourth minus 16. So we can rewrite our expression as a squared minus 4 times a squared plus 4 squared times a to the fourth plus 16 squared. Using the difference of squares formula, we know that a squared minus 4 times a squared plus 4 equals a to the fourth minus 16. So our expression becomes a to the fourth minus 16 squared times a to the fourth plus 16 squared. Now, let's continue our simplification. We can express this as a to the fourth minus 16 times a to the fourth plus 16 squared. Again, using the difference of squares pattern, we know that a to the fourth minus 16 times a to the fourth plus 16 equals a to the eighth minus 256. So our expression becomes a to the eighth minus 256 squared. Finally, let's expand the square of this expression. Using the formula for the square of a binomial, a to the eighth minus 256 squared equals a to the eighth squared minus 2 times a to the eighth times 256 plus 256 squared. Simplifying, we get a to the 16th minus 512 times a to the eighth plus 65536. And there we have it. We've successfully simplified our original complicated expression to a much cleaner form. A to the 16th minus 512 a to the 8th plus 65536. This example shows how powerful algebraic techniques can be in simplifying complex expressions. We've used factoring, the difference of squares formula, and other algebraic identities to transform our expression step by step. Let's summarize what we learned in this algebraic simplification process. We used various algebraic identities like the perfect square formula and the difference of squares. We factored and expanded expressions strategically. We recognized patterns that allowed us to simplify complex terms. We proceeded step by step, making the problem more manageable. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.